Well, hello, ap1. It's time for your chapter 3 video. This will be chapter 3, part 1. The first thing we need to talk about in chapter 3 is a little bit of math. We have to start talking about motion in 2 dimensions now. So we are now going to start working in 2 dimensions. The first thing we have to do before we can start describing motion and analyzing motion in 2 dimensions is learn how to actually deal with vector quantities. Remember, our vectors are mathematical devices that have both a magnitude and a direction. In 1 dimension, our directions were positive and negative, right? In 1 dimension, we had positive direction and negative direction. So our velocity could be negative 3 meters per second. That just meant it was going 3 meters per second that way. Positive 4 meters per second meant we were going that way. Well, in 2 dimensions, it's a little bit more complicated. In 2 dimensions, we have to look at both x and y directions. So positive and negative is not going to work because now we could be going these 2 directions. We could also be going these 2 directions, but we could be doing this. We could be going in that direction. Well, positive and negative is not going to do well at describing the difference between going like that and going like that. So we're going to need to use an angle. So for example, in 2 dimensions, a vector might be something like this. There is the vector, and it is in a direction equal to that angle. That angle, yeah, good. That's the Greek letter theta subscript a, by the way. So in 2 dimensions, our vectors are now going to be a magnitude, like always, and a direction, like always, but our direction is now an angle. So the way we're going to be writing vectors, for example, might be A equals 3 meters per second, and the direction of A is going to equal 25 degrees. By the way, we're going to measure our angles from the x-axis, from the positive x-axis. We're going to measure counterclockwise. So we're going to measure that way. Our angles will measure that way. Okay? So roughly 25 degrees for that one. So from now on, when we write vectors, we have to write them both magnitude and direction, but our direction has to now be an angle and not simply positive or negative. Alright. So let's start analyzing 2-dimensional vectors. I'm going to make another graph here. There's x-axis and y-axis, excuse me. And there's a vector A. Now, all vectors in 2 dimensions can be thought of as being created from or being the vector sum of an x component and a y component. For example, this vector here, A, which is in the direction theta, has an x component, which is that, and a y component, which could be written like that. So in other words, if I go from here to here, I can do that by using vector A. I can travel that length in that direction, and I go from point A to point B. I could equally well go this way, that length, and go in the y direction, that direction. So I can go that distance in the x direction, go that distance in the y direction, and I end up in the same place. This vector A is made up of an x component and a y component. This is a theme that we're going to play with a whole bunch in the coming months. A 2-dimensional vector has 2 components. It can be thought of as independently being an x component and a y component. Now, as a vector equation, we could write that the vector A is just the vector sum of the x component plus the y component. However, that equation is a vector equation. I want to warn you that this is not as simple as regular linear addition. You remember from trigonometry that the length of that side of a triangle plus the length of that side of the triangle in no way equals the length of that hypotenuse. Right? We're looking at a right angle triangle here. To find the length of that hypotenuse, it's not just x plus y, it's not just that plus that. This is in the realm now of our friend Pythagoras. And Pythagoras would say was that the length squared, that squared, is going to equal that squared plus that squared. That's our friend Pythagoras. Personally, I prefer writing Pythagoras like that. I just remember it that way and it saves on a tiny bit of algebra. But whatever. So, what we have to do is figure out how to actually do some of the vector addition properties, right? So, let's keep going. I know now the length of the vector can be determined if I happen to know the length of the two x and y components. Pythagoras will tell me the length of that main vector. But how do I determine the two components to begin with? How do I determine those individual components to begin with? Well, that is going to require us to remind ourselves of SOHCAHTOA. Our good old right angle triangle friend SOHCAHTOA, which stands for some old hag carries a huge tub of ale. Kidding. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. So, how does this work for us now? Well, if I want to, I could look at this vector right here. There's my vector A. And if I look at the sine of that angle, the sine of that angle is going to be the opposite over the hypotenuse. It's going to be the opposite over the hypotenuse. That's what the sine of that angle is. So let's write that. The sine of that angle is going to be the opposite, which is the y component, over the hypotenuse, which is the main component. If I do a little bit of algebra, I can solve that and say that AY is just going to be the vector itself times the sine of the angle. That gives me a way to determine the y component of a vector. I take the length of the vector itself, multiply by the sine of its direction, and I get the length of the y component. If I look at cosine, I can see that the cosine of the angle is going to be the adjacent times the divided by the hypotenuse. So the cosine of my angle is going to be the adjacent divided by the hypotenuse, so the x component over the hypotenuse. So that's going to be the ratio of the adjacent to the hypotenuse. If I do a little bit of algebra, I can solve for the x component by noting that that is the vector itself times the cosine of the angle. That gives me a method for calculating the x component. I take the length of the actual vector, multiply it by the cosine of its direction, and I get the x component. Now I have a way of calculating the y and the x components. What does TOA give to us? Well, the tangent of the angle is defined as the opposite over the adjacent. So if I want to, I could calculate the actual direction of that vector by taking the inverse tangent of the opposite over the adjacent. And that gives me a method for calculating the direction. So at this point, I can calculate the direction of a vector if I know the two components. I can calculate the two components if I know the vector itself and its length and its direction. And I can always use Pythagoras to actually find the length of a vector if I know the length of its two components. So those things all combine into just about everything we need to know about analyzing a two-dimensional vector. The only thing left to do is actually learn how to deal with taking vector A, adding to it vector B, which of course would be equal to some vector that we shall call the result. R for result. So how am I going to add a two-dimensional vector A and a two-dimensional vector B together? Well, this is going to require a method called vector decomposition. And I'm about to show you vector decomposition, and you will eventually be quizzed on your ability to perform vector decomposition. So, vector decomposition. Let's just take a couple of vectors here. Let's just draw a quick picture. So we have, say, vector A, and that's going to be in direction A. And let's take vector, hold on, I want to redo this. Let's take vector A shallower, it'll be easier to make a point out of this. And that's going to be in direction A. We'll take vector B, which is definitely longer, and going to be in the direction vector B. So we have those two vectors, and I want to add them together and get some result. Well, the short version is I'm going to take the x component of A and the x component of B, and I'm going to combine those into some resulting x component. I will then take the y component of A and the y component of B and combine them into some resulting y component. Then I will have an x and y result that I can use with Pythagorean theorem to get the actual length of the result. Let me diagram this for you. I would take, let's put this on a single graph here. I think that'll be a better way to look at it. I'm going to redraw those two vectors on a single graph so you can see sort of pictorially what I'm talking about. I will have vector A, and then vector B is long and steep, and I'm going to put the label for A over here. Okay, so what I will do is I'm going to take the x component of A, and I'll take the x component of B. Now I know that x component of B would actually be right here. I'm just drawing it here to make a point. Okay, what we will say is that AX plus BX is going to equal my resulting x. In other words, that whole thing combines to be my resulting x. Next thing I'll do is I'll take my result, my AY, which is that length. I'm just drawing it over here. I will then take BY, which is that. And remember, BY is going to be this piece. I'm just drawing it over here. And those two will combine to make a vector of length RY. So we will say that AY plus BY has to make RY. Okay? Then, once we've done that, I will now have this vector Rx and this vector Ry. So I will have Rx and Ry. Oops. And Ry, and what I want to do is combine those using Pythagoras, right? I'm looking right now at a right angle triangle. X and y are perpendicular. So if I do Pythagoras, I would say that the length of vector r is going to be the x component squared plus the y component squared, all square rooted. And that would give me this hypotenuse, which we will call vector r. The only thing we need to know now is that direction. And the way we can get the direction of a vector is with the inverse tangent. The direction of that vector will be the inverse tangent of the y component over the x component. Okay? So that was vector decomposition. Right now you're probably thinking, oh my God. But rest assured, when we are sitting in class together, I'm going to do an example of this live and we'll reinforce it. I just wanted you to see it once before we do it live. So as far as I can tell, we're going to conclude there and we will see you in class live.